In a groundbreaking revelation, scientists are unlocking the mysteries of quantum entanglement, at least in theory. A team of researchers has demonstrated that entanglement operates according to universal laws that permeate across all dimensions. This discovery has significant implications for multiple fields, including advancements in quantum error correction and fundamental physics. Executive summary. Researchers have derived a universal formula pertinent to Rényi entropy within conformal field theories, particularly valid as a certain parameter approaches zero. This formula applies to vacuum states characterized by spherical entanglement regions, simplifying the calculations for quantum information dissemination. A distinct formula applicable to two-dimensional systems has been developed, using a technique called the hotspot method, which is valid for any value of the aforementioned parameter.
Although this work remains theoretical, its ramifications could extend into the realm of quantum computing, error correction, and even our understanding of spacetime itself. Fukuoka, Japan. In an astonishing exploration of quantum physics, a team of scientists has unraveled a remarkable phenomenon where information within a certain category of quantum systems appears to entangle in a mathematically predictable manner. This marks the first rigorous formulation of a universal equation that describes this behavior, shedding light on one of the most perplexing aspects of quantum theory, entanglement. The collaborative effort from theoretical physicists at Kyushu University, Caltech, and the University of Tokyo has led to the publication of their findings in the prestigious journal, Physical Review Letters. They present a systematic approach to deriving a previously speculated formula that delineates the behavior of Rényi entropy in conformal field theories, CFTs. CFTs are a specific class of quantum systems noted for their high degree of symmetry. Rényi entropy serves as a mathematical instrument for quantifying the extent of information shared between two components of a quantum system. When particles become entangled, knowing the state of one provides immediate insights into the state of the other, regardless of the distance separating them. By honing in on how this information disperses through the system, the researchers managed to extract a precise formula applicable to instances where the entangled area is spherical in shape, and the system is in its lowest energy, vacuum state, specifically as the parameter n tends towards zero. A consistent framework in quantum information distribution. Using sophisticated mathematical techniques, the physicists demonstrated that across all CFTs, the degree of entanglement, expressed as Rényi entropy, adheres to a consistent rule when approaching the zero limit of the parameter n. Although this may sound technical, the core implication is straightforward. In these targeted quantum systems, information disperses in a reliable manner, irrespective of the specific characteristics of the particles involved. This established pattern depends solely on the geometric shape of the boundary delineating the entangled regions, along with a constant tied to the system's energy attributes. It can be likened to baking a cake. No matter what ingredients you choose, if you use a spherical baking pan and begin with cold batter, the time and temperature ratios will always follow the same ratios. Discovering the pattern, the influence of thermal thinking. To unveil this pattern, the team employed a methodological approach known as thermal effective theory, which treats quantum systems as possessing a temperature-like property, even when they aren't actually warm. This ingenious method allows physicists to simplify calculations that might otherwise be unmanageable, focusing on the overarching behavior of the entire system rather than tracking each individual particle's movements. Moreover, they uncovered how the entanglement spectrum, that is, how information is distributed across varying energy levels, aligns with expectations derived from other domains of quantum theory. Their findings not only possess aesthetic elegance, but also harmonize with established principles of physics. Interestingly, the research indicates that two-dimensional systems behave differently compared to higher dimensional systems.
In 2 dimensions, a distinct formula developed using the hotspot method is universally valid for any n value. In contrast, higher dimensional scenarios do not permit a straightforward application of the hotspot method due to the complexities arising from temperature-like effects at the boundaries of entangled regions. Lead author Yuya Kasuki, an associate professor at the Kyushu University Institute for Advanced Study, remarked, "This study serves as a pioneering instance of applying thermal effective theory to quantum information. The findings illustrate the potential utility of this method, and we aspire to expand upon it to enhance our understanding of the intricate structures behind quantum entanglement, implications for quantum computing, and more. While these findings are currently theoretical, they hold promise for future real-world applications." Quantum computers rely on the properties of entangled particles to execute calculations that traditional computers cannot manage. By gaining a deeper understanding of how entanglement functions, engineers could create more robust machines and develop superior error correction techniques. Additionally, the methods explored in this study may offer insights into the fundamental fabric of spacetime itself. Some cutting-edge theories posit that space and time emerge from underlying patterns of quantum entanglement. If this notion proves true, the new derivation could serve as an essential element of a broader cosmic puzzle. The authors note that the boundary thermal effective theory presented here is remarkably adaptable, suggesting that their methodology may well be applicable to a range of other systems in future inquiries. Closing thoughts. In summary, while the study presents a significant advancement in theoretical physics, it primarily applies to a specific set of mathematical models, namely conformal field theories, and should not be interpreted as experimental validation. The practical possibilities mentioned, such as advancements in quantum computing or theories about spacetime, remain speculative and warrant careful interpretation. Section: Paper Overview. Methodology. The research team employed thermal effective theory to investigate Rényi entropy within conformal field theories. They concentrated on spherical entanglement regions in their vacuum states, operating within the mathematical limit as the parameter n approaches 0. This enables the derivation of a universal formula that facilitates simplified calculations by likening quantum behaviors to that of hot gases. Results. The investigation confirms that Rényi entropy respects a predictable and universal formula under specific conditions as the n limit approaches 0. This relationship solely relies on the boundary area of the entangled region rather than the quantum system's specific particulars. Meanwhile, a separate formula from the hotspot method applies universally in 2 dimensions for any value of n. Limitations. The study substantiates the universal formula exclusively for spherical entanglement regions and when n approaches 0. Although the authors hypothesize that similar principles may extend to other geometric shapes, such assertions have yet to be verified. The hotspot strategy, effective in 2 dimensions, is not applicable in higher dimensions due to boundary intricacies. Funding and acknowledgements. Numerous institutions supported this research, including the U.S. Department of Energy Office of Science, the Walter Burke Institute for Theoretical Physics at Caltech, the Simons Investigator Grant, JSPS Grants and Aid for Scientific Research, the Inamori Frontier Program at Kyushu University, the Kavli Institute for Theoretical Physics, and the Aspen Center for Physics. Publication details. Title: Universality of Rényi Entropy in Conformal Field Theory. Authors: Yuya Kasuki, Hiroshi Uguri, Sridip Pal. Journal: Physical Review Letters, Volume 135, August 5, 2025. DOI 10.1103/FSG7Q. A note from Study Finds Analysis. Recognized for our clarity and precision, our Study Finds Analysis articles exemplify the blending of AI insights with human editorial expertise. Each article is meticulously reviewed to ensure accuracy and accessibility, blending advanced technology with traditional scholarly interpretation. As recent studies demonstrate, AI can assist in understanding complex scientific research as effectively as seasoned experts, making our platform one of the first to embrace this transformative help. We continuously refine our processes to provide top-quality content and invite you to review our AI policy to learn more.